Hey everybody, in this video, we will talk about phase changes. Phase changes are the changes that occur when matter transitions from one state to another. Let's first take a look at this phase change diagram that compares temperature to the amount of energy or heat that you add to a substance. In this case, the substance that we are looking at is water, H2O. So let's take a look at what happens at the beginning. So at the beginning, you're adding heat and the temperature is increasing. But suddenly, once it hits this point, once it starts melting, notice how the temperature stays constant while you're still adding heat. How can that happen? And then after it becomes a liquid, then it just heats up as normal and the temperature increases. But then once we go through the phase change, notice how the temperature stays constant once again. So there must be something up with this. And before we continue, let's label the different parts of the graph. This part is when it is a solid, this part a liquid, this part a gas, and this part is when liquid and gas is at equilibrium and they're fighting to, decide whether it's going to be a liquid or a gas. But during this stage, there are both liquids and gases because the liquid is slowly turning into gas. Or maybe if you're trying to cool it down, the gas might be turning into a liquid. Now over here, there's another equilibrium that occurs between the solid and the liquid as it is melting or freezing depending on the situation. So let's now talk about what actually occurs when you add heat to a substance. So initially when you add heat, the solid will rise in temperature, which corresponds to increasing the average kinetic energy of the particles in the solid. Since if you remember, if we increase kinetic energy, we are increasing the temperature. Now, once a solid reaches its melting point, or the point when it starts transitioning from a solid to a liquid, then it will stay the same temperature until it has transformed into a liquid. So, what's up with that? Well, if the heat added to melt a solid does not change the temperature, then the heat must be going somewhere. And you're absolutely right. The heat goes somewhere, and it doesn't go toward the kinetic energy. It actually goes toward the potential energy for the solid. And adding potential energy to a solid or liquid allows the particles to break the intermolecular forces holding it together. And in the case of a solid, it allows a solid to have its particles be looser, and once the particles are looser because of the increased potential energy, then it becomes a liquid. So in other words, phase changes correspond to an increase in potential energy and not kinetic energy. So the temperature remains constant during phase changes. Now you might be wondering, how does increasing potential energy cause the solid to become a liquid? Well, there's a very good explanation to that. The potential energy that we could think about in this case that holds the atoms together is the electrostatic potential energy or the electric potential energy. They're the same thing. So when you increase the electrostatic potential energy by adding heat during the melting phase, then the atoms are going to get farther apart. And remember, the atoms are attracted in the first place because of proton-electron attractions between two atoms. And as you add heat, the heat is being converted into electric potential energy, and this causes the atoms to be farther and farther apart. And when atoms are farther apart, they are more loose, which allows them to maybe be a liquid, for example, instead of being a solid. So if you're confused on why increasing potential energy causes atoms to go further apart, you can think of it this way. If something is moving towards something that it naturally wants to go to, then the potential energy decreases because the object is going to a more stable state. It's going to where it wants to go. But if an object is moving away from the direction it wants to go, that means that there's an increase in potential energy. So a great example to demonstrate this is gravity. When you lift an object up, it's going the opposite way it wants to go, which is obviously back down. And because it's going the opposite way it wants to go, it is increasing in gravitational potential energy, which is one form of potential energy. In the same way, two atoms are attracted to each other, and when you force them apart, you are increasing the electric potential energy, and this causes the atoms to go farther apart, which is why it is necessary to increase the potential energy of atoms when they transition from one state to another. So now we know how the science works behind phase changes. Now let's take a look at another topic that is very related. So when we go from solid to liquid, it is called melting or fusion. When we go from liquid to solid, which is the complete opposite to that, then it's known as freezing. And if we go from a liquid to gas, it's called vaporization. And the opposite process from a gas to a liquid is condensation. And then from a solid to a gas, it's sublimation. And you might be like, whoa, solids can become gases? Well, yes, they can. And I'll explain why in the next unit. And the opposite of sublimation is deposition, which goes from a gas to a solid. Now, we won't be dealing with these two just yet. We will be dealing mainly with these four processes. And if you're wondering how sublimation looks like, take a look at this image. Here you have iodine solid, which is I2 solid, that is transforming straight from a solid to a gas. So that's why I don't really see any liquids. You see, of course, the purple cloud of gas and the black iodine crystals. So this is a great example of sublimation. Now, let's talk about how math is involved when we do phase changes, because using math to describe things is a great way to describe things. So, in the previous video, we learned a lot about deltaH. So why don't we just learn more about deltaH? For a mole of substance that is transitioning from the solid state to the liquid state, and this is also known as the fusion process, then there's a deltaH fusion for that process, which tells us how much heat is needed to melt 1 mole of solid. So remember, deltaH is always 1 mole. Don't forget that, because that's very important. Now, the deltaH of vaporization, also known as the heat of vaporization, and deltaH of fusion can also be called the heat of fusion. Now, the deltaH of vaporization is the energy change or the enthalpy change involved when 1 mole of liquid becomes 1 mole of solid. And remember, this is increasing the potential energy, since during phase changes, the potential energy and not the kinetic energy increases. Now, of course, we also have a deltaH of sublimation, and this is just the energy or enthalpy change when something goes from a solid to a gas. Now, why is deltaH sublimation equal to the deltaH fusion plus the deltaH of vaporization? Well, we could easily use Hess's law to prove this. So, this first reaction, reaction 1, goes from a solid to a liquid, and that's the deltaH of fusion. For reaction 2, it is going from a liquid to a gas, that's deltaH of vaporization. And if you combine these two reactions, the liquid form of the solid, which we just generically call A, cancels out, and we're left with a solid becomes a gas, and then that is equal to the deltaH of fusion plus the deltaH of vaporization, since that is Hess's law, and this is equal to the deltaH of sublimation, which is describing this process. So we kind of just proved that the deltaH of sublimation is equal to the deltaH of fusion plus the deltaH of vaporization through Hess's law. So that's something cool that you could do with Hess's law. And don't worry, we will do that a little bit more in the future. Now let's get down to, let's first talk about how this works. So during this part of the graph, you are going to use deltaH of fusion, and on this part of the graph, you are going to use deltaH of vaporization, since these two involve phase changes. Now, what about these green areas? Well, these green areas, or these parts where the temperature increases, just involves a matter being heated and having its temperature increased, and this is most related to Q equals mcΔT, since Q is the energy or the heat, and the temperature increases alongside it, and this is most related to Q equals mcΔT. So for these green regions, you are going to use Q equals mcΔT, and C will be the specific heat for the substance, such as water vapor, for example. And yeah, so just be aware that for different parts of the graph, you are going to use different types of calculations to see how much heat is needed to, do certain process. For example, this process takes this much heat, this process takes this much heat, and they involve different types of math to, calculate. So just keep a note of that, and now let's take a look at this. The deltaH of fusion is equal to negative of the deltaH of freezing. The deltaH of vaporization is a negative of deltaH of condensation, and the deltaH of sublimation is a negative of the deltaH of deposition. Now, the reason why they're negations of each other is because they are opposite processes, and I could prove this right here. So let's just say that a solid A becomes liquid, and that's the deltaH of fusion. Now, what if we wanted to switch it around? How about go from the liquid state to the solid state? Well, if we flip a reaction, the deltaH becomes negative, and apparently the negative deltaH of fusion is equal to the deltaH of freezing. So therefore, we just proved that opposite processes have, opposite deltaHs with the same magnitude, but with a different sign, of course. Now, let's talk about whether these processes are endothermic or exothermic. Well, if you think about it, for fusion, a solid is becoming a liquid, and to do that, you have to add energy to the molecules in order to increase the potential energy and, break those intermolecular forces keeping them together, which is caused by the electrostatic forces that are making them attract in the first place. So, because you're adding energy to make a solid become a liquid, or a liquid to become a gas, or maybe even a solid to a gas, then fusion, vaporization, and sublimation are all endothermic processes. Meanwhile, their opposite processes, freezing, condensation, and deposition, are exothermic processes, because if you think about it, to get from a liquid to a solid, which is freezing, you are going to have to release some heat in order to get the molecules to move more slowly and to have lower potential energy so that they could become a solid. So that's the logical explanation to why freezing and the other two are exothermic. And note that endothermic is a positive deltaH and exothermic is a negative deltaH. So before we continue, I need to mention one thing. What is the difference between evaporation and vaporization? Well, evaporation is the same thing as vaporization in terms of what happens, but evaporation happens below the boiling point, and vaporization happens at the boiling point. I know that's not a very nice at, but you get the point. So I think now that we're done talking about the math involved and the science behind everything, let's now do a practice question. Let's find the amount of heat that is needed to turn 101 grams of ice at 263 Kelvin to 607 Kelvin. Now, it won't be ice anymore at 607 Kelvin because it would have already gone over the boiling point, but we have to keep that into account when we do the math. So I think the first thing that we could do is convert these kelvins to degrees Celsius, since we want it to match the melting points and the boiling points of water that are given to us. So 263 Kelvin minus 273.15 will give us around negative 10 degrees Celsius. Now I added the point because there are 2 sig figs in our answer when we subtract it, since there are no decimal places at the bare minimum, because this has no decimal places. Now, what about 607 Kelvin? Well, 607 minus 273.15 gives us 333.85, but we have to keep track of sig figs, so we have 0 decimal places, so it will be 334 degrees Celsius. Now, I already see a lot of sig figs going on, so I'm kind of worried about that, but let's just be careful, and I think everything will be fine. So, let's think about what happens when ice is at negative 10 degrees Celsius. So, let's actually first take a look at our information. We're given the specific heat for ice, water, and water vapor, which corresponds to this part, and this part of the graph. And we're given the deltaH of fusion for water and the deltaH of vaporization for water, which is here and here. So far so great. And we're given the melting point of water, which is 0 degrees Celsius, and the boiling point of water, which is 100 degrees Celsius. Now, to be honest, this, and the specific heat of water should be memorized, because water is one of the most common substances that we deal with when it comes to heat. So it would be in your best interest to memorize those 3 numbers, because we use 4.184 in calorimetry all the time when we're doing coffee cup calorimetry, and we should know the boiling and melting points of water, because maybe you're cooking and you gotta know that stuff. So, important information that you might need to know. So let's think to ourselves, what exactly happens? So let's use this table to, help us keep track of things. So let's just say this is negative 10 degrees Celsius, and let's just say that this is 0 degrees Celsius, because that's the point when it freezes or melts, right? So it's logical for this point to be 0 degrees Celsius. So what is the change in temperature when this happens? Well, we could do some math. We could say the final temperature is 0, and we subtract it from negative 10 degrees Celsius, and we get that the change in temperature is 10. So we could use Q equals mcdeltaT to see how much heat the ice absorbed in the form of kinetic energy, since this part of the graph is when the kinetic energy or temperature is increasing. So Q equals M, 101 grams is our M, okay, and our C is going to be 2.11 for ice, and our delta T is going to be 10. And let's actually put a point there, because we got to keep track of our sig figs. So when we do that, let's type this into a calculator. 101 times 2.11 times 10. We get that the change in heat is going to be about, 2 sig figs, so 2.13 times 10 to the third joules. Now, after the ice reaches that point, you have to add some heat to turn it from a solid to liquid. So in the second part, this first part over here is going to be heating the solid. Now we have to worry about the solid to liquid. So from the solid to liquid, we have to use the deltaH of fusion, which states that there are 6.01 kilojoules per mole of ice melted. So how many moles of ice do we have? Well, what's the molar mass of ice? Or, ice is just water. So water, H2O, has a molar mass of 18.02 grams per mole. And doing the math, 101 divided by 18.02 gives us about 5.60 moles of water. So we have this many moles of water, and each mole of water needs this much energy to, be melted. So we just have to multiply by 5.60 moles, and the moles cancel out, and we're left with, I have no idea. Let's just type into a calculator. And in your calculator, you probably have 5.60488 Now just keep that when you're doing your calculations, because keeping more numbers in your answer will give you more accuracy at the end, but just keep a note that you have to do sig figs at the end, which kind of tones down the accuracy. So doing the math, I get 33 point, it's going to be 3 sig figs, so 33.7 kilojoules. And we want to make this in joules, so let's make it in joules. 33.7 times 10 to the third joules. And I'm just trying to match the units. And in order to make the scientific notation, we can just move one decimal place to the left. So 3.37 times 10 to the 4 joules. Now that we're done with that, let's talk about the second stage it goes, or the third stage. So the third stage is when it goes from a really cold liquid to a really hot liquid, and this is related to Q equals mcΔT. So let's do step 3. So step 3 is heating up the liquid. So, Q equals the mass of the liquid water, which is 101 grams, because when you heat up stuff, the mass doesn't change. Fun fact. And the specific heat is always 4.184 joules per gram degree Celsius. And the delta T, well, what is the delta T? We're going from negative 10 degrees Celsius to 334 degrees Celsius. And so far on our journey, we're at 0, and we go to 100 degrees Celsius, which is, the boiling point. So the change in temperature would be, 100 minus 0, it's going to be 100. And in order to keep sig figs consistent, how about this? Let me put a decimal place there, because, you might think that this has 1 sig fig, and it might have 1 sig fig, but by putting the decimal place there, I'm making this number have 3 sig figs, and this just makes the math come out more nicely. So this will be 100 point as our delta T, and in the end, we get that the change in heat for heating a liquid from, 0 to 100 degrees Celsius is 101 times 4.184 times 100, and we get 4.23 times 10 to the, 4 joules. Now we have to consider the liquid to gas, and this is vaporization. So the heat of vaporization is 40.65. So, we have to do 40.65 kilojoules per mole of water. And how many moles of water do we have? Well, we have 5.60. So if you have it saved in your calculator, you could use that number that you used for the deltaH of fusion, which was 5.604, and, I might as well just use that. So using 5.60488 times 40.65, we get that the change in heat needed to, vaporize the liquid water is going to be 228 kilojoules. And let's make this in joules. So 228 times 10 to the third joules. And we move the decimal place 2 times to the left, and that will be 10 to the 5th joules. So I'll get there, but we are not done, because we're only at 100. We want to go to 334 degrees Celsius. So 334 degrees Celsius. And what is the delta T for that? Well, 334 minus 100 is going to be 234. So for the gaseous state, it wants to go Q equals 101 times the specific heat for water vapor, 2.00. So 2.00. And the delta T is going to be, well, I think I wrote it up there. It's going to be, no, I didn't write it. Well, I said it. So it's going to be 234. And that means that the Q, when you're heating it up as a gas, is going to be, 4.73 times 10 to the, 4 joules. So now that we have all the heat calculations done, let's add this all together. So notice how I added up all the processes that required heat together, and that will equal the total amount of heat that is needed to get the ice from one temperature to another temperature, and at that point it would be water vapor. So these are the 5 numbers that I added up, and to keep track of sig figs, you have to do quite a few things actually. What you have to do is make it so that there is a common factor that can factor out of each of these terms. So I decided that the term that I want to factor out is going to be 10 to the 4. And to do that, I have to convert all of these so that they are in the form of a number times 10 to the 4. And I did that in this step. And notice that over here, everything has 10 to the 4 now. So you could factor that out, and you're left with the numbers that have the sig figs, and you simply just add them up and keep track of sig figs. Notice how this has 1 decimal place, so your final answer will have 1 decimal place as shown here. So you get 10 to the 4 times 35.3 joules, and converting that into scientific notation, your answer should be around 3.53 times 10 to the 5 joules. And the only reason why I was able to add this all up is because they were all in joules. And that's why at the beginning, I decided to convert all my kilojoules to joules so that in the end, I could add them all up in terms of joules. So, nice thing to do. And this problem was extremely long, and no problem should require that much work. But in this case, some problems do require that much work. So that's all for this video. Have a nice day.